Okay, so let's start with the cyclist problem. Okay, so two cyclists leave from the same position. Cyclist A travels north at 10 miles per hour. 1 hour later, cyclist B leaves from the same position and travels east. Diagram theorem problem, we see a right triangle. Okay, let's just get all the calculus out of the way. The diagram theorem. Derivative. Remember, time is the independent variable here, so every variable is getting impacted by t. Okay, so let's get the rates out of the way here. Cyclist A travels north at 10 miles per hour. Yeah. dt. Positive or negative? Positive, right. Starting at the same position here, so we're expecting both x and y to increase, right? Everything is increasing. The triangle is getting larger. Every side length is getting larger. Cyclist B moving to the right, causing x to increase, positive. Okay, so dc dt is what we're looking for. We're looking for the rate, that distance between the two cyclists are changing. Okay, so let's do the easier one first. I think the easiest one is cyclist B. How far away is cyclist B after 2 hours?
40 miles.
Yeah, 40 miles, right? He's traveling at 20 miles per hour. 1 hour, he'll be 20 miles away. 2 hours, he'll be 40 miles away. Okay, any questions here? So by the time cyclist B has put in 2 hours of riding, how long has cyclist A been going on? 3 miles. 3 hours, right? 3 hours. So 3. So what do you think? How far is this cyclist A going to be? Good. Right. He's traveling at a lower speed, but for longer periods of time. 10 times 3, 30 miles. Right, that's the hard part. The hard part is just trying to figure out logically, where the cyclists are in the time period. Any questions so far? Mm-hmm. Yeah. But that's the hard part, right? If you can get that down, everything is going to be easy. Pythagorean theorem to get z, and then the rest of it, use the equation. Okay. Okay, a squared plus b squared equals c squared. Also, we recognize this as 3, 4, 5 triangle. $2,200 divided by 100. We get a positive rate, just like what we expected. Yes. Oh, okay. The reason why is because yeah, so cyclist A is going to start writing, and then an hour later, cyclist B is going to leave. And then 2 hours after that, so if you count that up, cyclist A would have been going on for 3 hours. We were writing for 3 hours. Okay, everybody okay? All right, number 2. Cone problem. As soon as we see cone, we know we have to be dealing with proportions here. 8 feet tall. Diameter of 10 feet. Okay, set up our proportions here. Radius of the small cone is to the radius of the large cone, as the height of the small cone is to the height of the large cone. Okay, the reason why we have to do this is because if we look at the volume equation, as water is being pumped in, we expect that radius to be changing, we expect the height to be changing. We can't replace any variable with any number because it's continually changing. So the best that we can do is to replace one variable with the next in the hopes that we get this right side to be just in terms of one variable so that we can actually find the derivative so that we can actually have enough information to plug in for all the missing variables. Okay, so cross multiply. We can come back to this because we don't know exactly which variable to solve for. We hope to gather some more information here. Okay, if the water is being pumped in at a constant rate of 3/5 cubic feet per hour, okay, what do you think that's referring to? Yeah, you see cubic feet, that's a big hint. Per hour, that's time. So you got volume, you got time, must be dV dt. Positive or negative? Pumped in, right? Water is increasing inside the tank, so rate of change is positive. At what rate is the depth of water in the tank changing when the tank is half full? H equals 4. But we got to be careful here. This is a moment in time. Oh, that's right. Rate of depth. yeah, careful with this 4 feet. This is a moment in time. We don't want to use this too soon. One of the biggest mistakes I see is students want to use this, at the beginning. But if we put it in the beginning, then we're saying that the height is never changing. Okay, and I didn't really mean half full. I think I mean say that when the height of the tank is at height. So this is a little bit misleading here. So I'll make it more clear. But I meant for it to be h equals 4. Okay, so save until after the derivative. Do not use until after your derivative. Okay, but these are big hints. We know that ideally things will be smoother if we can get our volume equation in terms of h. If we have our volume equation in terms of h, it will naturally produce these variables that we want to use. So that's going to help guide our path here. We would prefer to solve for r so we can get the r to be replaced. Solve for r here. So if I can get that r to be replaced, this piece will go in here. Okay, I think this is the hardest part of the problem here. So any questions? Did we see why we are doing this? Okay. Next step. The cleanup effort is also important. Notice we have not done anything with calculus yet. We're getting to the point so that our calculus power rule will be nice and easy. Mm-hmm.
Why are you finding?
Depending on what I'm asked to find. If I'm asked to find, if I'm given h or if I'm trying to find dHdt, ideally I would like my equation in terms of h because it'll produce dHdt faster for me. But if I solve for r, I can still get to dHdt. I just have to go through a little bit of additional step. I have to find the derivative here. 8 drdt equals 5 dHdt, and I can convert from one rate to the other. But if I can look ahead to see what I am going to need, that's going to help guide my initial efforts. Okay, so the biggest mistake I see students want to enter 4 into the starting equation, which we don't want to do. The second biggest thing is students want to find the derivative a little too early. Okay, we could find a derivative, but why go through product, chain, and all that messiness if we can go further? Okay, but what I see is students want to do power rule here. They get a bunch of DHDTs together, and that's not quite correct. Okay, we have to spend the effort to clean this all the way up so that we can find our derivative correctly if we just want to do power rule. Okay, so let's clean this up here. The 5 needs to be squared, the h is squared, the 8 is squared. Okay, that's still a mess. We're still not ready. Okay, all the coefficients need to be nicely placed together. The h's are going to be pushed together as well. Use your calculator. Leave pi out of your calculation. 25 divided by 3 times 64. Make sure you merge the h's together. So I want you to see this is where we want to be. This is, if we can get it cleaned up like this, we're going to find the power rule to be the easiest part of the problem. Okay, but you have to get it cleaned up to that point so that we can have an easy calculus process. Okay, from here everything becomes easier, but the hard part is trying to get to this point. So any questions I can answer about this point here? Okay, so when you're studying for the test, really try to see if you can work these problems from scratch, right? Can you gather all that information, work it all the way down? Okay, so now we're ready. V, now we're ready for our derivative. V produces derivative, dv dt. All this mess is just a coefficient that hangs out in front. And then h cubed is really the derivative that we were after here. H cubed becomes 3h squared dh dt. Okay, you're welcome to do a little bit more cleanup, but you can also start putting information in. Okay, now the 4 is ready to be entered in. Now the dv dt is entered in. Now we can solve for dh dt. So you see how this everything comes out so nicely? If we make the right substitutions, everything that's produced is ready for us to solve and for us to plug in. All right, so, okay. dv dt is 3/5. H is 4, now we're ready for 4. Okay, clean up as much as you can here. I got it all the way down to 25/4. The calculator helps me get to that point. Divide by 25/4 to get to the other side. Dividing by a fraction is the same thing as multiplying by the reciprocal. Notice pi is in the denominator. What's our unit of measure? 8 per hour. Okay, it's a lot of steps, but hopefully with the fact that we've been kind of doing this ever since the second day of related rates, hopefully you're getting more comfortable and you're able to see where all the pieces go. Yes?
Do you do a linear approximation of a possible problem?
Yeah. Okay. Got it. Okay, are we okay with this problem though? All right, so let's skip over then to the related rates test review. And let's look at 6 and 7. We'll do a linear approximation here and we'll do a limit problem here. Okay, so limits. What's the first thing we do regardless of plug in the 1? Let's see what's happening there, right? If we plug in the 1, if we get a real number like 0/5 or 3/4, we stop. There's nothing more to do. There's only more work that needs to be done if we get 0/0, if there's a hole, if there's an indeterminate form. Okay, so what happens when we plug in 1? Okay, we do get 0/0. This tells us that there's a hole. There's a limit that exists. We just haven't found it yet. Normally, we would try to do factoring, but now we have L'Hopital's rule available to us. And the whole purpose of L'Hopital's rule is we're going to use the derivative to produce hopefully an easier expression for us to reevaluate so that we don't get that 0 over 0 anymore. We get something that is real number related. Okay, so derivative, what's x cubed minus 1? Mm-hmm. Denominator? Okay, as soon as you apply L'Hopital's rule once, you have to reevaluate. The tendency is students, they want to keep finding a derivative. They'll say 6x, then becomes 6, and then they want to get it all the way down to a ratio, and then that's being the answer. Sometimes that is the case, but you always want to pair each 0 over 0 gets one L'Hopital's rule. Okay, so as soon as we do L'Hopital's rule here, what's next? Yeah, plug in, right? So 1 in for x. Okay, do we get a real number? Three over 11, no. Okay, are we good with the process for L'Hopital's rule? Now, let's say I got a 0 over 0 again. If I got 0 over 0 again, that means I can take the derivative again once. Okay. Okay, number 7 is a linear approximation problem, but it'll be worded a little differently. Let me word it a little differently for us so you can kind of see what it'll look more like. Let's say our function is 1 over the cube root of x at x equals 8, and then approximate f of 8.04. This is more like what you're going to expect in terms of the wording. This is a very compact form of this question, but I'll word it more spaced out like this. Okay, so let's think about the strategy here. Plug in the 8 to get the order pair. That will be your point. Get this ready for derivative, power rule. Once you find the derivative, the 8 goes into the derivative to get the slope. Once you have your order pair and your slope, point slope form, once you have your tangent line equation all nicely set up, then the last thing to do is to fill the x with 8.04. Okay, I'll go through the steps here. Okay, order pair. You guys good with that? Okay, what's next? Slope. So slope comes from the derivative. To get to the derivative, we need to do a little bit of cleanup here, right? Make this x to the 1/3 in the denominator, which is really x to the negative 1/3. Okay, power rule. Okay. What can we do once we have our derivative? Find the way. Yeah, find the slope, right? 8 into the derivative will get us our slope. This is cube root of 8 squared. Cube root of 8 is 2, 2 squared is 4. Oh wait, I messed up here. This should be negative 4/3, my bad. I need to subtract 3 over 3. Cube root of 8 is 2. 2 to the 4th is 16. 16 times 3 is 48. There's better. Okay, so we got our two big important piece of information here. We got our point, we have our slope. Now ready for point slope. Get y by itself, and then finally we can insert that 8.04 in. So the important thing is get to that tangent line equation. If you can just keep telling yourself, all right, just get to the tangent line equation, and everything after that will be easy because I'm just literally just going to insert my decimal into my tangent line equation. So it's not anything new. We just have a specific name for this thing that we're doing. Mm-hmm. Okay. Everybody good with this problem? So this is number 4, right above 6 and 7. Okay, street lamp is mounted on the 15-foot pole. We're always going to set up the same way. It's always a triangle within the triangle. Always looks like this. The only thing different is filling in those vertical components there. Set up our proportions. Always have to identify our small triangle with our large triangle. So we say height of the small triangle is to the height of the large triangle as the base of the small triangle is to the base of the large triangle. Okay, are we good with that? Okay, cross multiply. Just get all of our equations, derivative out of the way here. Easy equation, should be an easy derivative as well. But we don't just want to say 6 equals 9, right? Time is always going to be kind of sticking around here. So 6 dx dt. Okay, let's see what information we can gather here. Man walks away at a speed of 5 feet per second away from the pole. What can we assign that number to? Good, dx dt positive 5, because as he's walking away from the lamppost, that distance between him and the lamppost is increasing. How fast is the tip of the shadow moving? Okay, so ultimately, if we can just find dy dt, we can get to the tip of the shadow. But let's find the shadow length rate first. Okay, do we have enough to solve for dy dt? Yeah, 5 goes in for dx dt. We solve for dy dt. And then finally, if we want to find the tip, we just add the two rates together. Okay. So rate of change of the tip is always just going to be dx dt plus dy dt. Okay. Part B, find the rate of change of the area. I meant to say area of a large triangle. At this moment in time. Okay. What's the formula for a triangle? Let's think about that. Yeah, so area is 1/2 base times height. Okay, what's the base? We're talking about this space right here, right? What's that length going to be? Good, x plus y. What's the height? Right? Okay, can I clean this up where it'll just be a nice, easy power rule? I can rearrange it, right? Maybe put the 15/2 together and distribute it through. There's really no need for product rule because I can separate everything nicely here. Okay, no need for product rule here. dAdt equals, what does x become? Everything that we have gathered before is still usable. Just have to put it in this formula here. Oops, 10/3. Oh, rate of change. Oh, what's our unit of measure here? Good, feet squared. Feet squared represents area. Time component is seconds. Let's do a area circumference problem here. Kind of like pairing two different equations. So number 3. Okay, we know we have to involve both derivatives. Let's go ahead and just find all that information. We may not need everything, but it's just nice to have everything in front of us. Pi r squared becomes 2 pi r dr dt. Circumference. Okay. Everybody okay with creating those derivatives there? Okay. The radius of the circle is increasing at a constant rate of 0.2 meters per second. What can we assign that to? Say it again. Is it dc over dt? It says the radius of the circle is increasing, right? So dr dt. Okay, radius of the circle is increasing, so okay. You see the word increasing, keep it positive. What is the rate of increase in the area of the circle? Now we're looking for what? dAdt. at the instant when the circumference of the circle is 20 pi meters. Okay, so we know our target. We know that we're trying to solve for dA dt. If I can just find a numeric value for r and a numeric value for dr dt, then I'm sitting at my answer, right? So dr dt, that's nice and ready for us. But I don't know radius. Is there a way for me to get to radius? Good. So my link is circumference equals 2 pi r. I can use this information to solve for r. If I solve for r, I'm ready. I can insert all that in. Radius is 10. Clean this up. 1/5 times 10 is 2. 2 times 2 is 4. Or use your calculator, it's fine. Units of measure? Meter squared per second. Yeah. So, oh, great. Thank you. Okay, number 4. Cylinder. Whenever you see a cylinder problem, you should automatically think this is going to be easier than cones. Okay, and it's different than cones. Okay, so the biggest mistake I see is we do so much cone problem that we want to translate the cone process into cylinders. Okay, so we should have an easier time with this problem. Okay, cylindrical tank has a height of 16 feet. Water flows at 8 cubic feet per minute into the tank. Okay, what is that assigned to be? Positive or negative? Positive. Area of the circular base is 25 pi. How fast is the water level rising? What are we looking for? dHdt. When the tank is half full. Okay, what's the first order of business with cylinders? What's the big thing that sets cylinders apart from cones? Radius is constant. So that's the first thing you want to do is find the radius, get the radius to be removed, just get it out of the way, right? Cones, we can't quite do that. We know that we have several moving parts, so we have to make the appropriate substitution. But here, we know the radius is a constant. Let's just get it out of the way. We can't just quite remove it. We'll replace it with a number, but it'll make our equation easier to work with. Now, they don't give us radius directly, but is there something related that can help us get to the radius? Right, we have area of a circle, and then we're going to use that to help us get to the radius that we need. So there is an extra step in this problem here. Good. So that's a big thing with cylinder problems. The radius is constant. There's no need to hold on to that variable if we know it's never going to change throughout the entire problem. So just want to replace that radius to begin with. I can't do it with cones, but I can do it with cylinders. Okay, so your volume equation should look a lot cleaner, a lot easier to work with. Okay, we're ready for the derivative. Minimal cleanup here. Okay, V becomes dv dt. 25 pi h becomes do we have everything we need? Yes, 8 inserts into here, and we're ready to solve for DHTT. Divide both sides by 8. Notice pi is in the denominator. We just have to leave it there. Units of measure. Feet per minute. Okay, easier problem, right? But careful. Are there extraneous information here that we did not need? And what else did we not need? Well, why should we needed that? Yeah, because we needed that for the radius. There's something else that did not come into play for us. The height of the water level and the height of the container. Neither are used. They're perfectly used for cones, but they are there as distractors for cylinders. So just be careful, right? We don't want to get caught trying to think, oh wait, how do I? So I think this is what students do. They see this and they say, oh, I got to use that somehow, and so that's what's leading them to creating proportions in similar triangles, because they feel like they have to use this. So it's an easier problem, but then there's a lot of things that distracts us from making the right decisions. So I want to point those things out. Okay. Any questions? I think I may just go through, maybe I'll focus more on the related race test review, but I feel like, yeah, I don't have many more problems. I'm probably going to be redoing some. So if you've attended all the help sessions, I think you should be good. The test review that I gave you guys that we worked on in class, I find that's the best review. If you can do that from scratch, from beginning to end, you should be pretty good. Okay. All right. So I'll hang around if you have any individual questions. Yeah. Oh, yeah. This is my last time, right? The one that we did, which is. Okay, see you.
Thank you. Do you know how to do the circle and the square?
No.
And do you think the test review that we received like last week is better or the one that we did today?
I think they're kind of similar, but I guess the test review that we did before has everything in it, and it's like 4 pages, so I think that's better. But I mean, I think you've seen most everything, so it should be okay. LJ, how do you feel?
I get like most of it.
Oh, yeah. The morning is not going to play a role in travel.
Because it would be like the same
Because
as the project.
Right, because if we were to use it, we would have to use it at the derivative level, and the derivative doesn't have any excess of life. That tells us that it doesn't have any. Okay. Okay, see you tomorrow. 1/2 base times height. So 1/2 base is x plus y, and height is.
Oh, okay.
So if I rearrange it, I'm going to get 1/2 15 x plus y, which is really 15 over 8. Okay, see you.
That makes a lot.